welcome to the deep dive. We're starting today with something pretty startling, actually. A prediction that by 2050, nearly half the entire world population could be nearsighted, myopic.
It's huge. And, it sounds like just needing glasses, but it's often much more than that. We're talking about a real health crisis brewing.
More than an inconvenience, then.
Absolutely. High myopia isn't just about blurry distance vision. It comes from the eye physically stretching, elongating too much. That axial elongation carries serious risks, things like retinal detachment, myopic maculopathy, stuff that can genuinely threaten sight.
And the cost, both economic and just, well, human cost, is immense.
Staggering. And while it's global, East Asia is really feeling the brunt of this epidemic.
Which brings us right to our mission for this deep dive. We're looking at a really important study, one that tries to give eye care professionals a critical tool, basically objective data.
That's right. We're zeroing in on eye measurements, specifically axial length, AL, and the ratio of axial length to corneal radius, ALCR. This study gathered data from thousands of Chinese kids and teens aged 4 to 18.
Okay, so the big question we're tackling is, how do we move beyond just asking better now or now during an eye exam? How can we use precise objective numbers to actually predict who's at highest risk and needs help before it gets bad?
Exactly. We need to forecast, not just react. And that starts at the physical eye. AL, axial length, is simply how long the eyeball is front to back. Myopia fundamentally happens when that length outpaces the eye's focusing power.
It's a mismatch.
A mismatch, precisely.
And the ALCR ratio, that puts the length into perspective.
It does. It compares the length of the AL to the curve of the cornea, the eye's main focusing surface. It's about how those two components fit together.
Right.
And here's maybe the first aha moment on why this biometry is so important. Traditionally, we diagnose myopia using refractive error, the glasses prescription number, right? But subjective refraction, the better 1 or 2 part, it's only accurate to about plus or minus half a diopter.
That sounds like quite a margin for error, especially when you're tracking small changes in a growing child.
It is a huge window. But these modern biometers, they measure AL objectively super fast, and the error is tiny, like down to a few microns. It's night and day in terms of accuracy. Objective, quick, reliable.
Okay, so let's get into the methodology here. This study sounds massive. A retrospective look, pooling data from 3 earlier studies.
Yeah, data from 14,127 participants. That gives you incredible statistical power to see the real trends.
14,000.
Wow.
And they didn't skimp on getting accurate baseline measurements, I gather.
Yeah.
Cycloplegic refraction for everyone.
Correct. They use eye drops, like cyclopentolate, on all 14,000 kids. That's critical.
Explain that for us. Why are those drops so non-negotiable, particularly with kids?
Well, young eyes are focusing powerhouses. They can accommodate, adjust their focus really intensely, sometimes too intensely.
Right.
So without the drops, a child might appear more nearsighted than they actually are because their focusing muscle is working overtime. It's called overaccommodation or sometimes pseudomyopia. The cycloplegic drops just temporarily relax that muscle, so you get their true baseline refractive state, no muscle spasm messing things up.
Got it. Clean data is key. So they have this mountain of accurate data, and then they need to make sense of it, turn it into usable charts. They use something called the LMS method.
Yeah, lambda mu sigma. It sounds technical, but it's basically a statistical smoothing technique. Imagine just plotting all 14,000 data points. It'd be a mess, right? Yeah. The LMS method lets you model how the distribution of measurements, like eye length, changes smoothly with age. It creates those nice percentile curves we need for tracking growth and predicting risk.
Oh, that makes sense. And those smooth curves revealed something really important about which measurement to focus on. The ALCR ratio being better than just AL alone.
The numbers really back that up. When they looked at how well each measurement correlated with the actual refractive error, the spherical equivalent, or SE.
That's the glasses prescription number.
Exactly.
Hey.
The ALCR ratio had an R-squared value of 0.83. AL by itself was lower, at 0.70.
Now, 0.70 to 0.83 might not sound like a huge leap to everyone. What's the practical difference?
Oh, it's significant clinically. It means that just by adding the corneal curvature into the equation, you're explaining about 13% more of why a child has the prescription they do. It really confirms that the eye's overall focus depends on that interplay, the length matching the front curve. The ratio captures that balance much better.
So, length relative to the cornea paints a clearer refractive picture. But wasn't there a catch related to age?
Yes, absolutely. This was fascinating. They looked at how well the AL percentile matched the ALCR percentile for the same child. In the really young kids, like at age 4, the concordance was actually pretty low, only 0.13.
13%. That
Yeah,
low.
yeah. But it got much better with age. By age 13, the agreement was up over 0.75.
Okay, wait. If they barely agree at age 4, that sounds like a major warning for clinicians screening preschoolers.
It really is. It strongly suggests that using AL alone isn't very reliable for figuring out growth patterns or refractive state in those very young children. Their corneal shape is still changing quite a bit relative to their eye growth.
So the ratio is even more critical in toddlers and preschoolers.
Indispensable, I'd say. That the cornea's role is just disproportionately large in those early years.
That really shifts the focus for early screening, doesn't it?
Mhm.
Okay, let's talk about the big picture growth patterns from these 14,000 kids. The general findings were kind of expected for this population, right? Eyes get longer, ALCR increases, kids get more myopic with age.
Yes, the overall direction wasn't surprising, but the spread of the data is where it gets interesting. They looked at the range of eye lengths at different ages. So at age 4, the difference between the shortest eyes, the third percentile, and the longest ones, the 95th, was only about 2 millimeters.
Pretty tight range.
Very tight. But then, as the kids got older, that range just widened significantly. By age 18, the gap between the third and 95th percentile for AL was almost 4.5 millimeters.
Wow, it more than doubled.
It did.
It's that widening spread.
Mm.
It really makes you think about environmental factors, doesn't it?
Mm.
Like maybe genetics sets a narrow starting range, but schoolwork, screen time, less outdoor time, that's what stretches the distribution out later.
That's exactly the implication. It suggests those external pressures are differentiating the cohort over time, pushing some kids much further down that path to high myopia.
Okay, and then there's the gender difference piece, which had a real twist.
Right. So statistically, females in the study had shorter axial lengths.
Okay, shorter eyes.
And they also had steeper corneas, on average, than males.
Shorter AL usually means less myopia risk, though. But that wasn't the case here.
That's the counterintuitive part. Despite having shorter eyes, the females actually had more myopia. Their average refractive error was more nearsighted.
Really? How big a difference were we talking? Say for the same eye length.
It was quite striking. Take an axial length of exactly 24 millimeters. For females with that eye length, the average prescription was 1.47 diopters. For males with the same 24 millimeter length, it was only medifly 0.26 diopters.
That's more than a full diopter difference for the same physical length.
It is.
That throws a wrench into the simple longer eye equals more myopia idea.
Yeah.
What does that imply?
Well, it means you can't just look at AL, even with percentiles. For any given AL or even ALCR value, the female eye in this group seems predisposed to be more myopic. Part of it is the steeper cornea adding focusing power, but the size of the difference makes researchers think something else is also contributing. Perhaps the crystalline lens inside the eye has more power in females, on average.
Like an internal accelerator for myopia, even with shorter eyes.
Potentially. It suggests that interventions just focused on slowing down eye growth might need different calibration or expectations for females.
Fascinating. Okay, this next comparison really drives home why these specific Chinese charts are needed.
Yeah.
How did this cohort stack up against European data?
The difference was stark. Chinese children had longer axial lengths at basically every age compared to European kids, and that difference got bigger as they got older.
Longer eyes overall. But the really shocking part was the speed of growth, wasn't it?
Yes. The rate of change, how much the eye elongated from age 5 up to adulthood, was about 2.5 times faster in these Chinese children compared to European children.
2.5 times faster.
It's a massive difference. It highlights that we're dealing with fundamentally different growth trajectories. You just cannot use European norms or general charts to monitor these kids accurately. You'd miss the rest completely.
That makes the case crystal clear. Okay, so that leads us right into the practical use. We have these charts, this data. How does it actually help a clinician day to day? Let's talk prediction.
Right. The big shift is moving from just saying myopic or not myopic to actually calculating the probability of myopia based on age, gender, and where they fall on these AL and ALCR percentile charts. It's about risk stratification.
And the model they built using all those factors worked pretty well.
Very well. Overall accuracy was strong, sensitivity around 86%, specificity about 84.5%. For the main school ages, 5 to 18, it was even a touch better. So it's a reliable screening tool.
And how does that compare to, say, just checking vision on a chart without drops or non-cycloplegic refraction?
It's comparable or even slightly better in terms of accuracy. But the huge advantage is that biometry measuring AL and CR is super fast, it's objective, highly repeatable, and doesn't need as much skilled manpower as doing careful refractions on lots of kids.
Much more efficient for large-scale screening. Triage the risk effectively.
Exactly. Now, let's hit the statistic that, for me, really changes the game. It completely reframes what we think of as normal growth in this kind of high prevalence setting.
You're talking about the risk for kids right in the middle, the 50th percentile.
That's the one. We tend to think 50th percentile is average, typical, probably fine, but not here. At age 10, if a child was at the 50th percentile for the ALCR ratio, their chance of already being myopic was around 30 to 37%.
That's already quite high for an average 10-year-old.
It is, but watch what happens as they go through the main growth years.
That gets worse.
Dramatically. By the time these Chinese children hit age 15, if they were simply tracking along the 50th percentile curve, perfectly average for this population, their probability of being myopic was greater than 95%.
Wow. Let me just pause on that. Over 95% risk at the median by age 15?
Yes.
That means average growth is the high-risk trajectory in this environment. If you're seeing a 15-year-old in urban China and their measurements are bang on the 50th percentile line for their age and gender,
you should be thinking about myopia control intervention almost certainly, not just watching and waiting.
It completely flips the script. Average is the new danger zone. It makes proactive management essential.
Confirms the need for early and maybe even aggressive intervention for statistically normal kids in these populations.
Okay, but we need to be clear about what this tool can and can't do.
Right.
It's great for spotting risk, but are there limitations?
Definitely. While the model is excellent for predicting the likelihood of someone being myopic, it's not so precise at predicting their exact glasses prescription, their SE. The researchers calculated the 95% confidence interval for estimating an individual's SE, and it was pretty wide. Plus or minus 1.78 diopters.
So almost a 2-diopter range either way. You definitely wouldn't want to prescribe glasses based only on the percentile chart reading.
Exactly. That's the boundary. Use the charts to flag the kids who need attention, who are on that risky growth path. Start the conversation about control strategies early. But don't use it to determine the final prescription. It tells you who to worry about, not precisely what correction they need today.
That's a crucial distinction. Okay, let's try to wrap this up for you, the listener. The core message here is that these new specific percentile charts for axial length and, importantly, the ALCR ratio give us vital objective tools. They help monitor eye growth way more effectively than older methods, especially in places like urban China where myopia is so common.
And that ALCR ratio really is key, particularly for the youngest kids, where just looking at length alone can be misleading.
And that, truly stunning finding. Tracking at the 50th percentile, just average growth, puts a child at over 95% risk of myopia by age 15. It forces us to redefine normal in these high-risk groups.
It does, but there's always a what's next. And here's something to think about. This entire study, powerful as it is, used cross-sectional data.
Meaning one snapshot in time for each child.
Exactly. Thousands of snapshots. But still, just snapshots. It's like looking at a huge crowd photo instead of watching a movie of one person growing up. That limits how well we can truly project an individual's future risk.
Right, because we don't see their personal speed of change.
Precisely. And think about environment, too. This data is from urban China. We know lifestyle matters for myopia time outdoors, near work. How well would these specific percentile values apply to kids in, say, a rural setting, even within China, or to different ethnic groups with different environmental exposures?
Good point. The absolute numbers might shift.
They might. So the really critical next step, the thing for you to ponder, is what happens when we start layering longitudinal data, tracking the same kids over multiple years onto these kinds of charts. Can we then create truly personalized growth trajectory predictions? That's where the field needs to go to really tailor myopia control for each child.
Combining the population snapshot with the individual's motion picture. That would be the goal.
Yeah.
Definitely food for thought. And that brings us to the end of this deep dive.